So today we will do Sinkhorn based generative modeling. So this is based on optimal transport. Okay. So we have seen Wasserstein distance and we have seen this W PQ form where P is let's say real distribution, so P real, and Q could be parameterized by some theta, right? So image generation problem could be seen as a distribution parameterized by theta, and we are trying to make it go close to this in the sense of Wasserstein distance. So essentially this becomes minimum theta WP real P theta, okay, and obviously P theta, where theta is a parameter of the neural network. That's what is happening everywhere these days, okay. Neural networks are used wherever you can. So what we found in our earlier variant is we used KR duality, and from KR duality what we found is that W PQ is upper bound, or in this case let's say supremum of norm of H less than equal to 1. So this is like one ellipsis functions, and then expectation of Hx minus expectation of Hy. So this was the KR duality, and what this says is that given a Wasserstein distance, you can write this as a difference of the expectation of Hx and Hy, where H are one ellipsis functions. So basically you look for all possible functions H for which you see them as a difference of these, okay. So then overall if you look at the we have to minimize this, right, and then it's overall it's like so, and then within the Wasserstein there is a supremum problem involved, right. So basically it's sup and then min, or you can say inf theta, and then your let us say P is some real, right. So what you are trying to do is it's trying to kind of like looking for, or in this case since it becomes H eventually here, then it's like supremum over H, and then you are trying to kind of minimize this over P, and Q is like a theta, P theta. So Q is like parameterized by neural network, okay. So the other distribution. So this is how led us to this is how this thing led us to, and P obviously P theta obviously is like the generator, right. So this is how it went into a min-max problem where H is the discriminator and Y is seen as a push forward of the generator, okay. So overall this is a min-max problem of discriminator and then minus of discriminator, and then since discriminator is in this case we never use the classifier, so this is like a generator of X from the basically the and G takes the noise, right. So basically we do the noise, and X is for the generator and X takes from the real, okay. And this is how eventually everything boils down to minimize over theta, because generator is parameterized by theta. So this was one way, right. This was one way to derive a generative model, and what we got is W GAN, or Wasserstein GAN, okay. It involved going from Wasserstein distance and then using the KR duality. From KR duality we have these basically this min-max formulations, and then basically parameterization, okay. So these were like 3-4 steps needed to make it useful, okay, in practice. So what this other idea we will talk about is a kind of a direct approach, where by direct I mean we are not going to use KR dual. We will still start with Wasserstein distance, and what we are saying is there a other way? So one way was write this using KR form, and the question was whether you can supremize this over one ellipsis. Now what we are looking for is there another way? But there are other ways where we may kind of regularize this a little bit. It's called entropy regularization and things like that, and then it becomes tractable, at least in the discrete sense. So this is the theme of today's class. Okay, so Sinkhorn based generative model, and many papers have been published along these ideas. So one of the ideas is faster algorithm, which becomes competitive with state of the art. So some of the earlier results on this was style transfer using OT. So that paper got a lot of traction. So we will see this. So first of all, the basic idea behind this is optimal transport. So optimal transport is a problem of minimizing the cost of transferring one distribution of mass to another distribution of mass. But that is like, that's essentially what we have done earlier. Basically, we're looking to find an optimal distance between a good measure to find the closeness of two distributions, and this is exactly what generative modeling is also asking for. So this is not necessarily a one-to-one assignment problem that you study in algorithms or graph combinatorial style, right? So this is not necessarily even one-to-one assignment problem. So you can use some methods like Hungarian algorithm and things like that. So there are algorithms that do this optimal matching. Okay, but here it's a bit different. Here it's about even matching the distributions. So it's a little bit more in the sense that rather than saying one-to-one matching, we are also asking for sometimes some splitting can happen. So this guy has more. So let us use the word mass, meaning resources. Okay, so in terms of probability distribution. So sometimes it's the numbers here may not be equal to the number here. Okay. So here a B and this is A. So first difficulty is A is not necessarily equal to B. Okay, so it's more about distribution being matched rather than point-to-point assignment. Okay, point-to-point assignment is a very special case of optimal transport. So here sometimes splitting is required. Okay, so some part of the mass went here, but some part of the mass went here. Okay. So or sometimes joining can happen. So these two mass combine, and let us say factory and mining is also a very common thing. Mining and factories. Okay, so you have many mining places, and then you have many factories. So it's not necessary that all the, let's say, coals, right? So all the amount of coal from one mine necessarily has to go to only one. Okay, sometimes splitting can happen, and obviously when the splitting happens, then the conservation of mass should work. Okay, and it should work both ways, in the sense that all the factories should get what they want, and all the mines or the coal that was produced was also used up. Okay, so there are like two ways constraint going on here, and one can essentially make a matrix. So these are like factories F1, F2, and these are mines M1, M2. So what we are essentially saying is that these row-wise sums should match. So if this mass, the coal produced taken from mine 1 is taken from is given, some part is given to F1 and some part is given to F2. So in this case, let us say half and half. Then obviously whatever amount M1 had, it should match up to the quantity of M1. Okay, so this row sum should be preserved. Okay, and it's the same thing we can say also for the factories. Okay, so whatever capacity they have, so F1 needs certain F1 capacity, then it should be fulfilled by the mines. But in whatever fraction they get, it doesn't matter. Okay, so this is a slightly more interesting problem than the mere assignment problem that you see. Okay, or even more generally, it's like even distribution matching. So right now we are thinking in terms of discrete case, but one could also see this in terms of continuous probability density matching. So this is my density, and this is my density. So I am asking for which of these, what is a density that is closest to this. Okay, so in the continuous case, it becomes even more interesting and even more hard. Okay, so but for all practical purposes, what happens is that we work in a discrete sense anyway. Even if someone gives us continuous, we in real life we work with samples. So so with the samples we take some expected values and we estimate the mean, sample mean, and so on. So even if I take a normal distribution, which is a continuous distribution, but at the end of the day, I'm working with samples, and then I will be working with sample mean and things like that. Okay. So let x, p, and yq be some finite probability spaces with x is n and y is n. So already we are saying that they may have like the different numbers. Okay. So if you are going to, so one have like m, another is n, and then let pi pq be the collection of probability distributions on the space xy, okay, with marginals p and q. So now we are looking at this notation pi pq. So these are all set of all probability distributions, okay, with marginals p and q. So in the discrete case, what you can say is these are all matrices. Okay, so we know that joint PDF is given by a tabular value. Okay, where I have some p here and I have some q here. Let's say these are marginals. So these joint distributions in the discrete case, you can always visualize this. In all the rest of the class, you always see this pi pq as a set of matrices, and this set of matrices are such that the column sum is q. Okay, q1, q is like, you can see this as a vector, right? So this q2 and so on, and the row sum is p1, p2. So this p is a marginal, and this q is a marginal distribution q. Okay, so you can visualize throughout the class today, we'll be using this quite a lot, that these pi pq are essentially joint PDF, but in the discrete case, joint PDF is like a matrix. So it's saying I take a sample xy, it's like throwing two die. Okay, so how do I get joint PDF? Joint PDF is essentially like throwing two die. Okay, and then when I draw two die, then the samples I get are pairwise samples, right? D1, D2. Okay, so it's like I throw two die, and then I say I take samples outcomes D1 and D2. Okay, so these are the joint probability values we are looking at. Okay, so but these in our case, there is this this constraint, obviously, that the marginals, these are all set of matrices, obviously, but all have the constraint that the row sum and column sums are p and q vectors. Okay, or for all of them. Okay, that's what this notation means. Okay, so if this is clear, then this will help a lot in the next class. I mean, then in the next slides. So now another thing we want, because we are looking at optimal transport, obviously when I move one distribution to another distribution, then I will look for some cost of that, right? So let us say that cost is denoted by C. Okay, and since cost usually it's some kind of a norm, then it will be some positive greater than equal to 0. Okay, so then the optimal transport problem is now defined as this. So this is basically the distance, and we have this sub C here, that obviously this distance depends on the type of the cost that I'm going to take, and this is a minimization problem over the, remember the set of matrices. Okay, so you can visualize this a set of matrices, but then it's like I can also make this matrices into a long vector. So if I make this into a long vector, then like this I can make this also as a long vector. Okay, then I can make this as a one big pi vector. Okay, and then I will look at the cost also as one big vector, and then I do a dot product of this. Okay, so that's like so what I'm saying is like when I sample, I get pairwise values here, right? And so I get a pairwise values x1, x2, and so on, and something like that, right? So in my joint sample space, I have pairwise values, and then what I'm saying is like, what is the cost between these pairs? Okay, so so then in that sense, I can kind of vectorize them, or if you are still okay with the idea that I can think of matrix times matrix dot product, then it's fine, okay, because usually you learn dot products like this, right? So either way it's okay, you flatten it, make it a vector, and also the cost is 1v vector, the same length obviously because you are taking a dot product. Or you think of this as same size as a matrix, just like in convolutions we did, and you do matrix inner product, okay? Essentially means flatten and then inner product, or reshape it back, okay? So that's fine. If that notation is okay, then this problem, optimal transport problem, is essentially minimize this dot product, okay, over the pi. So basically your problem is like, yeah, there are many possibilities of this joint distributions for a given marginal. I have uploaded a document with an example in Moodle where it's possible that for a fixed marginal P and Q you can have multiple joint, okay? So that's that we know. So basically this problem is about minimize over all possible joints, okay, all possible joint distributions with marginals P and Q. So and this basically, yeah, so this we want to do this for all possible x and y that's there, right? So in terms of matrix, then what it's saying is this matrix is there, and then we have this these pi xy value. So this whole pi is this whole matrix, right? And then let us say P1 has 3 components. So P sample space of P1 has 3 outcome possibility. So let us say this 3-sided die, P2, P3, and then there is a 2-sided die. I mean, it may not make sense physically, but let us assume for the moment it's like this, okay? So it's like, as you see, we have allowed M to be different from N. So this could be my x possibility, sample space. In this case, this is my y. So my sample space y is 2. So then obviously xy here refers to all possible things here. So here you have 1 1. So x 1 1 possibility, 1 2, 1 3, 2 1, 2 2, 2 3. And basically that inner product essentially is that, okay? So basically what we have done is that we have expanded this inner product, and what this essentially means now is that in the matrix form, so if I use the same matrix but maybe I have a bigger space here, then this is like C of x1 y1, and then the matrix values there, pi of x1 y1. So this is my first entry. So C of x1 y2, and then pi of x1 y2. So this is my second entry, C of x1 y3, pi of x1 y3, okay? So these are multiplied, right? And similarly I will fill these values, okay? And then I am supposed to sum up, and what I am asking for, you are allowed to vary the pi, okay? And then tell us like what is the outcome of these, okay? So so this is what we are trying to minimize in this. So you could have also written this in terms of expectation. So essentially what this means is you can also see this in terms of other type of matching. So let us say this row and this block is there, and then we are kind of trying to match in some way, okay? Let us say we are trying to pair up the heights, okay, of someone's sampled randomly from here, someone's sampled randomly from here, and what I'm asking is on average, and let us say that the height is, in our case we are measuring the height, so I'm just taking the difference of height of one person from here, one person from here. So that's xy, and then my cost is like the usual distance, okay? So then I will take the difference. So what I'm asking in general is what is that matching that I should do among these two groups such that I will get this minimum cost, okay? So that's what is happening here. So I may change the permutation here, I may change the permutation here, and then I start matching. So obviously I have to do quite a lot, right, to find this pi. So so in this case we can say 2 norm. Yeah, so if we choose 2 norm, then there is a specific name given to that, and it's called W1 distance, okay? Wasserstein 1 distance. Okay, so this for this special case we will try to see how what we get. So just to clear the notation a little bit, obviously the marginal p is when I sum up the joint with the other variable, which in this case is y. Okay, so that is correct. So if I have a joint and if I integrate out or sum out the other one, then I get the marginal with p. Okay, so that's clear. And then I can write this in this form, right? Because at the end of the day, this is also a matrix, right? So summing up the y essentially means that let us say this is my y. So if this is my y and this is my x, then summing the y is same thing as saying that I multiply with a vector of all ones. Okay, so this is my pi matrix and this is my vector of all ones. Since there are m rows, so this is like m. Okay, and then it is essentially what I get as a result is p, which is also a vector, obviously. So we can see this as a matrix times vector, which if I multiply a vector of all ones on the right, then it means that I sum up the sum across the columns. Okay, so we are okay with these notations. So this is a vector of all ones. So this is what I have written again. Is the same thing. It's so basically we see this this as a dot product. Okay, so we see this like this as a dot product. Similarly, now we can look for marginals in y, right? So we did this for x, so the same by symmetry the same notations could be used, but in this case we are doing the row sum. So we will multiply vector of all ones, and this is our joint distribution matrix. So this is like 1 transpose. So this was, in general we see vectors always as column vectors. Okay. So by convention we always see all vectors as column vector. So in this case we want a row, so we did a transpose. So then it becomes like this. And then if I multiply this vector of all ones from the left to a matrix, then obviously it will do the sum across the rows. Okay, and which is what we want to get a qy. Okay, so this is the marginal with y. Okay, so with these notations, what we did is just notations, and then we can write this optimal transport with equality constraints. Okay, so our original problem is now written more compactly in this form. So we have these constraints that pi was not like anything, right? The way we choose pi was always like this. These are set of pi's with marginus p and marginus q, but then we in the discrete case we could write these as equality constraints, that the sum across the rows is across the columns is p and sum across the rows is q. Okay, so as such it looks like a nice optimization problem. You have a cost function there and you have some variable pi here. So C will be the cost function itself will be obviously fixed, whether you are taking a 2 norm. So this will be fixed anyway. Okay, so what really matters then is it's about pi. Okay, so what are the pi for which this optimization problem will have minimum value and this equality constraint is there. So that's equality constraint problem, and it's a linear program. So before going ahead, I think I have just a small remark that I also told you in the starting of the class is that P and Q, if they are two continuous distributions, then as I said in the beginning, that even if they are continuous, at the end of the day we are working with samples. So we will take a sample from the continuous P, we will say take a sample from the continuous distribution Q, and we will get an approximate distribution via histogram plots. Okay, so I took those samples and then I plot a histogram that gives me the frequency values and basically the for each sample what is the probability value I get, and then from there I can learn a approximate distributions P and Q. Okay, so here P tilde and Q tilde are distributions approximated from the observed sample. So continuous may be there, but you can always, if you have samples in hand, if you have a way to then do that, then you have these P and Q. And P and Q you need, because P and Q are the constraints. While you are looking for the joint distribution, you do want to look for only joint distributions for which marginals are P and Q. So you do have to know this P and Q. So in practice, if you're dealing with continuous distribution, you can always sample and get an estimated P and Q for the discrete case. So the discrete versus time distance can approximate the continuous one like this via P tilde and Q tilde. But although the original problem could be for continuous P and Q. Okay. So the last expression which we had, like the previous slide, we obtained for the optimal transport is a minimization problem with two equality constraint. Okay. So this minimization problem is equivalent to a linear program because linear programs are like the cost. In the cost, you have a linear objective, and which is the case in there, because the until now we did this, right? So this is a linear program because this is like some cost transpose pi. Okay, so pi is a variable in itself. So pi is in linear form, right? We are not taking square or any nonlinearities. So we can easily prove that C transpose pi is at least affine. You can prove. Okay, so this is an affine function. So hence it's a linear program, and it's also a linear program because the constraints are also equality constraints. So that satisfies this linear program category. So we may use LP solvers for optimal transport problems. Okay, we may use, but then in the original form, if you don't do any regularization, then you don't get. I mean, there is no guarantee that you will get to minimizer of such problem. So sometimes you are given a problem and you have to do some regularizations to make it work. Regularization could be that your original problem is not necessarily convex, but then after you add the or add some form of regularizer, it becomes convex. So then we say it's regularized because convex functions optimal point is unique. Okay. And if there are compactness arguments and everything is there, convexity, compactness, and then there is a guarantee that they will have a minima, and it will be unique. So as such, since we are here, so as such, it's a linear program. It's equality constraint. So obviously those are all part of linear program. A key development was made in around 2013 by Couturi, who proposed. Because until then people were struggling to even LP program is not necessarily like easy program. Okay, it is one of the well studied optimization problem. LP is not necessarily easy to solve. Okay, so a key breakthrough came by Couturi in 2013 in his paper, where he proposed this OT is entropy regularized OT problem. So until here it's OT, but then he added this additional regularization term, which is the entropy term. Okay, so entropy term is like minus x log x is called entropy, right? So there is a modification now, which is we call it OT entropy. Okay, so now you may say that when you regularize, right, so when you add some additional terms in your problem, is this well defined, and what about the original problem? Okay, did you change that too much? Okay, so here if you can see, as lambda tends to 0, DC so the OT regularized one, if you notice the notation, you have this additional lambda here now. Okay, the original OT problem was just DC. It depends on the cost, right? But now after regularization we have a lambda here. So this is OT regularized, entropy regularized OT, and this is the original OT distance. So what we are saying is that as lambda tends to 0, obviously as lambda tends to 0 here, this guy will go to 0, and what I will get back is the DC, okay, which is the original OT. So it may happen that while I am solving, I may want to prefer lambda to be very close to 0, so that I get to the original problem. Okay, so from numerical point of view, you may keep lambda to be small, and so on. Okay, because at the end of the day we work with approximations. Okay, these are all numerical algorithms. We always work with approximate ideas. Okay, because sometimes the exact solution and all this is not really tractable. So reframe entropy regularized OT problem as scale divergence, and this is the another. I mean, first thing was regularization. Regularization itself is a good thing, because if you see lambda h, my negative of the entropy is a strongly convex. Okay, so the first idea when you may have gone about such regularization is to somehow make this problem more more regularized, means like maybe strong convexity. So in this case, this is a strongly convex. Okay, entropy, negative of the entropy is a strongly convex. So if you want to see this, then this is like negative of x log x. Okay, so prove that fx equals to negative of x log x is strongly convex, meaning 2 times of derivative, 2 times derivative is positive. Okay, make sure that double derivative of f is positive. Okay, so and strictly positive. If that is the case, then this means that the second term that you added is a second derivative is strictly positive, then it's strictly convex, and the first term is linear, so overall it's strongly convex. So this could be the first intuition when I'm looking at an optimization problem. Can I bring in more stronger variant of convexity? So this just linear and having something which gives me existence and uniqueness, it's much more preferable. So that could be one thing when you're looking at. But then another thing is this relationship with KL divergence, right? So there we will do a small trick to arrive there. So first define kxy to be like this. Okay, e to the minus cxy divided by lambda. Okay, you define it a bit like this. Initially you will not see things clearly right now, but let us assume some k is there. Okay, obviously you see some terms, right? There is c there is lambda there. That's also there in the OT problem, right? And now you define a z lambda to be sum of the kxy. Okay, so it's a artificial way to create a distribution. So here you have this kxy, which is exponential of minus cxy divided by lambda, and then you are looking at the normalizing constant. So normalizing constant is when I sum up. So basically I want a normal form, right? So kxy kind of like normalized. So kxy normalized means like I divide by something that is sum over all the values of kxy. So that is being done here. So then we say that it's normalized, right? It's like creating a unit vector, right? So then if it is normalized in the sense that the values will be now between 0 and 1, that is the criteria for a distribution, right? If I have a case where all the entries are between 0 and 1, then we can term this as some distribution, let's say. Okay, because this guy is always going to be larger than denominator is larger than numerator, right? Because it's normalized, so it's between 0 and 1. Okay, so these are like probability values because these are between 0 and 1. So that's like and if I sum over this, then it is indeed 1. Okay, so that's what probability distribution needs, that each entries are between 0 and 1, and the sum is 1. That's it. So we got this distribution, although it looks like artificially created, but that will give a link, right? So now let us look into our familiar old friend DKL. Okay, so which is the KL divergence, and we with the fact that P lambda k is this is the P lambda k, right? That we just defined. Now we want to see how far is this P lambda k from pi. Okay, the joint with marginals P and Q. So by definition of KL divergence, we can write this is exactly the definition of KL divergence, which is basically means that you are taking an expectation rate of this log term, right? So by definition we know that the KL divergence of P and Q is P log P divided by Q. So that's what we did here. Okay, where our DKL PQ was expectation, or write this in the sum form, right? So it's Px log Px by Qx. So that was our definition of the KL divergence for the discrete case. It's a sum, and this is sum over x, and in this case In this case, it's a distribution with two arguments, obviously, but that doesn't matter. And that x could also be seen as a vector. So here we have this, and in place of p we have pi, and in place of q we have this guy. It was kxy divided by z lambda in the denominator, which was p lambda q, but then since z lambda was in the denominator, it went up here. Okay, so these are some simple things, and then we have this k divergence. Now let us see what really happens with this, right? So we will break the log, it seems. So we have pi xy as it is, and log of pi xy divided by kxy, right? So that log splits. So this numerator log is here, and the denominator, yeah, I think in place of k I also put now exponential term. That's why you see this guy showing up here now. And log and exponential got cancelled. Okay, and that is why you see only this guy now. Okay, so that's what happened, right? So this is like pi xy log of pi xy, and then there will be a plus term as well, which is written at the end, but okay, no problem. And then okay, let me do the plus term because I see z with this guy only, right? So let me dare that. So this like log of the product is we sum of that, right? So then we have pi xy and log of z lambda. So I did that, and now I will do, I'm going to work on the denominator, which is minus pi xy log of k xy. Okay, so this is what we did here. Here there is a little bit of a jump. So that jump is because I substituted the k as well. So now let us work only on this part. So this is minus xy log of kxy. So kxy was exponential, right? So e to the minus c xy divided by lambda. Now we all know that log and e gets cancelled. So eventually this gets cancelled. So what we get is pi xy minus of c xy by lambda, which is indeed here. Okay, and other terms are matching as it is. This guy is matching with this. This guy was here. Okay, so that's fine. So we have that, and so then we come here, and it seems like we wrote pi without xy, and just in a compact notation. Okay, because so we wrote this as a dot product basically. Okay, so here we are revealing each entries of pi, but then we can say let me see this as a vector. So then I just write it as a vector, and 1 by lambda. Okay, so this seems to be, yeah, this seems to be this term we are looking at. Okay, this is the term we are looking at. So here obviously minus becomes plus, and c became 1 by lambda came out here, and c was vectorized. So c is vectorized and pi was vectorized. So this is like dot product. And so we have seen that, right? Cost and pi we can maybe vectorize. So this part is done. So negative of entropy is this term, right? First one, I mean this one is negative of entropy, right? These are the form x log x, right? But then entropy is like minus x log x. So we put a minus here, right? So minus of the entropy pi, and then we have log z lambda. Oh, because log z lambda is independent of pi, right? It comes out, and if you sum over any distribution, right, it becomes 1, right? That's a property of a distribution. So pi being a distribution, this sums over to 1, and log z lambda has nothing to do with this. So this comes out, and let's pi does its own sum, and it becomes 1. So then you are left with only log z pi, log z lambda. Okay, so this is our status right now. Is we have, let us clean this up a little bit. So this is what we have as a. So what we found is that, so what do you notice, right? We started with KL divergence, right? And we created this artificial distribution. Let us keep that in mind. This was artificial created. So maybe you work in the background, okay, and play around a little bit, and then see what KL divergence of how pi looks in terms of some distribution that that was created here, right? So this additional insight comes after kind of like you play around a little bit. Okay, right now it's written, so you see how One would have thought like that, right? But you play around a little bit to see the connections between KL divergence and the original OT problem. So so we know that this is similar to the OT regularized problem. Only thing is the log is there, right? But log as such has nothing to do with pi anyway. So this part was the OT regularized problem. It's just that lambda is here in the denominator, but then that doesn't matter, because lambda 1 by lambda you can always take common, and then lambda comes here, okay, with the original form, and this guy has nothing to do with the pi. So you can even make it invisible. So essentially, because you will look at the minimization problem now, right? So if I put a minimum here, and this is a minimum over pi, and if I put a minimum here, this is also a minimum over pi. So in this minimum game, log pi has nothing to do with it. So that guy stays away. Okay. So then it's about minimum of this guy with this. So then and then in the minimum we know that 1 by lambda I could take common. 1 by lambda I could take common. So then this is like c pi minus lambda h pi. Okay, so this I can write it like this. Now again, whether I minimize a function fx or whether I minimize a function c times fx, it doesn't matter. C has no real role to play. In the place where I get c is positive, okay, so in the place where I get c fx minima, it will be the same place where I will get fx minima. So this 1 by lambda could be thrown away as well. So in the overall minimization thing, what you get back is this original OT problem, and this is what is written here. Okay, because at the end of the day it's the arg min, right? It's not just min. So what we are looking at, the argument where the minima was achieved, the pi at which the minima achieved. I was not interested in the minimum value. I was interested in the x for which fx was minimum. I was not interested in the minimum of fx. So that's why in the arg min thing, because obviously the minimum of cfx will be different from minimum of fx. But if I look at the arg min is the same. Arg min means as x for which the fx is minimized will be the same x for which cfx is minimized if c is positive. So that's why we could throw away quite a few things. With the same argument you could throw out log z, because it has nothing to do with the pi. The optimal pi for which optimal will be achieved, log was like a constant. So if you look at the arg min, then which is written here, right? So arg min of the KL divergence of pi with the artificial distribution that we created is indeed the OT entropy regularized OT plus entropy regularized, right? So that's that we get back, right, with this definition of P. Okay. So there is this connection between KL divergence and the OT with entropy. Now, what are the good things about entropy? I have already said this, minus h pi is strongly convex. So then you can take this as an exercise to prove that a linear, because original was linear and objective, and we added the entropy, negative of the entropy. So we have linear plus strongly convex. Prove that it is convex. So this is an exercise. You may use differentiability. So you can use second derivative test and prove that the second derivative is positive. Now with some assumptions on the set pi pq, and that is the set of all joint. And so another thing is like existence of solution, right? So basically we are looking for solutions from this space, right? We are looking for small pi, which is coming from this bigger pi, which is the space of joint distributions with margin p and q. So we are looking for one of the optimal pi from here, and then the question is does there exist such pi? From the compactness argument we saw in the previous class, it is guaranteed if I do fx minimize over fx, and then x is coming from some compact set, right? So by extreme value theorem that we saw, that the function that I am minimizing is continuous, a continuous function on a compact set attains its maximum minimum. Okay, so we are going there basically. So what we are saying is, in our case, x is pi, and pi is coming from capital pi, and so this space, if it's given to be compact, and what we are minimizing here is strongly convex. Convex function, is it continuous? Take it as an exercise. So then we have the extreme value theorem set up that a continuous function on a compact set. So essentially from maths point of view, we do have a guarantee of some sort. that minima will be achieved. So you may try some of these as an exercise I have mentioned here. So what does this all mean, right? So this says that there exists an OT plan, right, that achieves the minimum transportation cost, and few of these things are coming because of the entropy regularization. Okay, so we have the uniqueness. Okay, so if we squint a bit, the OT with entropy may help in generative modeling. Okay, so you may look at the optimization problem. It's like a KL divergence. So now you may even think of, in the beginning classes we had these, right? We were doing this KL where we had pi, we had P, and we were looking for Q theta, right? In almost all the generative models that we have seen so far, and also what we will see, almost all of them either start with KL divergence or Wasserstein distance. Okay, so at the end of the day, whatever regularization you did, and if it could be seen in terms of some measure like KL divergence something, you kind of have a hold on, okay, let me parameterize few things and let me use it as a generative model. Okay, so we will come to that. But right now let us keep our thought process with the optimization problem. So it may be used as a generative model. Okay, we will outline the things. So more on this later. So there is a geometric interpretation, but this geometric interpretation is quite evident because we are taking a dot product in some sense. So this is like an information projection of the cost matrix associated Gibbs distribution. Okay, projection of the cost matrix associated Gibbs distribution at temperature lambda onto the space of joints P and Q. And so yeah, so that's like because we see this as a kind of a dot product. So we have this geometrical view. So we have existence because of compactness, continuity, and we have uniqueness also because of the strong convexity. So all this is awesome, but is there any algorithm? Okay, what about algorithm to solve this optimization problem? Existence and uniqueness sometimes have nothing to do with how you are going to solve the problem. Okay, so we need to think about a way to solve this problem. Okay, so let us now kind of recap, like we do a little bit of warm up to derive an algorithm. So what we have in hand is this OT, entropy regularized OT. Okay, so we recall this again, we have already seen this before, and what we are looking for is a solution pi lambda, the small pi lambda, in the space of these marginals with joint with margins P and Q. So let us define some notation C. Capital C is, let us look into space of joint with only guarantee is that is like marginals with P is there. P marginal with P guarantee is there. So as if like row sum guarantee is sure, column sum guarantee is not there. Okay, so you may see this as one type of sets where marginals with P is there, and then another type of sets where the marginals with Q is guaranteed, but the other way is not guaranteed. So one way row sum is always P, but not necessarily the column sums. One way column sums is Q, but not necessarily the row sum is P. Okay, so what we could see is that this space breaks up into two intersection of these, obviously. Okay, because in this we are asking for both which marginals are P and marginals with Q. So basically we are looking at some form of intersection of two sets. Okay, so it's an intersection problem. Okay, can you start from some random point and get into the intersection of two sets, right? So now it becomes a nice intersection problem. Okay, and then the algorithm is like you start from some initial guess. Now again there are like many algorithmic questions. Can you start from a guess which is completely outside, or should you start from a guess that is in one of these guys? And how do you get to the intersection? Okay, of these. Okay, so then yeah, I mean one intuitive would be like you want to get closer to both, right? So wherever the point is, you may say that let me get the closest point to one set and then let me get closest point to another set, and then to another set, and you keep doing that until you hit some intersection point. So in this case, what might happen is maybe so maybe let us say this is my closest point. It may not be perfect that I have drawn, and then you may say, okay, from here what is the closest point to other guy, and maybe you will get to some intersection here. Okay, so from maths point of view, natural questions are there. What is the guarantee that you will get to the intersection point? So in fact, when you do this projection itself, there are some questions, right? Do you get this unique projections, right? Now this is also not necessarily guaranteed, right? So let me give you a set like this, and there is a point P here. Okay, so now if I ask you to project, by project we mean the point P is closest to some, it should be closest to some point in the set. Now this set, the way the geometry of this set is, it looks like it's going to kind of, okay, it's going to kind of give me make things a bit difficult for me, because as if like there are 2 points. Okay, and this is a bit problematic because after this moment you lose uniqueness, it becomes a ill-posed problem. Okay, then you might think about the problem itself, like what led you to this. Okay, this is the reason why you define your functions like that. You don't say one point is mapped to like 2 points. Okay, you remove those things, but in practice we might think like that, right? 1 point may go to. So these are redundancies that will be very difficult for you to prove, because if the things get splitting, there is no way for you to control the convergence and track it. Okay, so the question is, even this projection step, right? Is this a good projection, well-defined projection that is leading me to unique point in one set, another point, unique point in another set, and obviously this set itself, projection is one thing, and then whether this iterative way will really need to lead to some intersection point, right? So these are the things while thinking of algorithmically. So from for our problem, OT, entropy regularized OT, it is kind of like, yeah, I mean, first of all, it's a set we have already defined, C and D, but these sets as if they are like matrices. Okay, so the view here, it's more of a kind of like a matrix being kind of iterated. Okay, so this is the matrix view. Now there is an algorithm that I may not be able to cover today. I will take just 10 minutes in the next class, I guess, but that will do a further improvement on this. So what we are right now, what we are looking at is a matrix kind of view. So this is a space of matrices. Okay, and this is costly, obviously, right? Because I'm running these iterations on the space of matrices, right? So further improvement was done on this line, but we are starting with some basic approach. And what we are saying is, you start with some matrix as an initial guess, and what you are saying is like this is like pi q, and this is by pi p, right? So what we are saying is like, you may, I mean, it is not that hard to actually start from a point like this with marginals in Q or somewhere here. Okay, so it's not really hard to actually start from one of these. Okay, and because in some algorithm it may be actually needed that you start from there. Okay, so but yeah, so ideally, and so what is happening in our case is these points are like matrices, and we are looking for optimal matrices, right? So what we are saying is like, okay, from this random matrix that I have, give me a nearest possible matrix from here whose marginals are Q. Okay, and then from here what I'm asking for is give me a nearest possible matrix from here whose marginals are P, and then so on. Okay, so of course the way I have drawn is that they don't intersect, so that I mean, that is something that should be there in the assumptions itself, that the sets we are working with are indeed the ones. So in other words, there are joint distributions with marginals P and Q. It's possible. Okay, so then in that case there will be intersection. Okay, from the algorithm point of view, if they don't intersect, then at best you get into a closest point at some point, because what will happen is that you will do this and then you will get stuck here. Okay, so this algorithm kind of will at least give you the shortest distance between two sets. Okay, and all this works well with convex. So that's why I also said in the beginning, right? So all these projections and all these are well defined if it's a convex set. I gave you an example what goes wrong in a non-convex set. So if you remember the definition of a convex and non-convex, this was exactly the case of non-convex sets. Okay, because if I take two arbitrary points, the line joining them is not inside. Okay, and these kind of sets create problem in projections. Okay, so projections are well defined on a convex set. If you are given a convex set, projections will always give you a unique point. Okay, that's a good thing about convexity. So then in that case, now in our algorithm we want to kind of fill these things, like whether pi p was a convex set, pi q was a convex set. It's quite kind of evident, because pi p you are looking for set of matrices. So this is like an affine. Okay, so pi p are the set of matrices pi such that pi 1 is p. So these are like set of this is a affine space. Okay, so affine space is by default convex. So this is even simpler. Okay, so these are you can prove that this is an affine function. So I mean the space, you can prove directly that it's convex. Okay, you take 2 points pi 1 and pi 2 and prove that theta of pi 1 plus 1 minus theta of pi 2. If you do the one of this, it will also be p. Very easy to prove. Okay, so that could be doable. So this is a convex set, directly you can prove. So pi p, and same way you can say pi q is also a convex set. It's just that there is a row sum going on like that. So we already kind of know the set C and D that we are going to do alternate projections. They are necessarily convex. Now I am a bit relieved that I will start with any random guess. I will do projections. I will get to the unique projections, and then I will get to the intersection. So now we are all set for the algorithm. So we will define these this algorithm, which is nothing but just projections. Okay, so closed set we know already. Let us say C and D be the closed set, right? So closeness is good because we are looking at the distance of the points from the C. So the distance is the minimum function I'm looking for. And since these points are in the closed set, there will be a point which is kind of right there in the set itself. Okay. So closeness is guarantees that the point is there in the set. Okay. So so closeness necessarily tells me that I'm looking for distance from my current point to the other one. Then this indeed gives me a point in the set C, and similarly for D, and they are closed and convex. So all these good properties help me in a well-defined unique projections that I'm going to get. Okay. So after that, it's basically about alternating. So in this algorithm, we initialize it from one of the sets. So our initial guess is not necessarily from completely outside. Okay. So there is, let us say this is C and this is D. So we are saying that let my initial guess x naught starts from C, which usually won't be difficult. Okay. You may ensure that the matrix that you are initializing, you just make sure that the row sum is P, which is easy thing to do. Okay. So as long as you ensure that you are in one of the set, and then you have some projections defined, which projection in the simplest sense could be like, let's say, 2 norm. Okay. So you are looking for a 2 norm distance from the set. Okay. So like that, and then it will go there. Okay. So I define a projection that that gives me a point y, because this PD is a projection on D. So this means that I'm getting a point y from the D set. Okay. And and then I'm taking that y and then I'm projecting it back to the C set by the projector's PC. So then I'm getting a point xk plus 1 in the C set, and obviously I keep doing this. Okay. So this is odd and even. Those who are from Delhi, they know that, right? Odd even rule. So these are like even and odd thing happening here. Okay. So even number card and odd number card you drive. Okay. So this is a simple projections, and So this generates a sequence of points xk in C and yk in D. And obviously for this algorithm, what we are expecting that the intersection is non-empty, right? So this is in the argument itself, okay? If it so happens that they did never intersect, then obviously we cannot produce anything by this algorithm. So this is part of the assumptions that they do intersect. And then the sequences xk and yk both converge to a point x star in C intersection D, okay? So yeah, again, this is already covered. Now, what is the guarantee that PC and PD gives a unique point, unique output? So, convex set, and this point X is there. So, as a simple exercise, you can say the two norm distance. Let's say that defines your projection. Okay. So, the projection I will define one possibility is like this: projection on the C of the point X is minimum of y minus x, where y is in C. Okay, this is like two norm distance I'm looking at. Okay, and you may take this as an exercise that if C is a convex set, then the minimum point that you are looking for from the set C over which this distance gets minimized, and that will be there. It will exist and it will be unique. Okay, that's happening because of the convex outcome. Okay, so there is a guarantee. What if C and D are not convex? So I gave you already an example in the previous slide, and there is no guarantee that there will be unique output after projections, not necessarily unique. Thus, alternating projection finds a point in the intersection, provided they intersect. Okay, what if they don't intersect? I also gave you an answer. If they don't intersect, then you get to the closest point, closest distance between two sets. That's it. So you still get something interesting. Okay, so this was the original paper about this. So what I will do here is not prove that it does converge. So I'm skipping that one. I'm just stopping at the algorithm for the moment. But this proof was long time ago. So this proximity maps for two convex sets. So this was by authors these. So they say here the method of successive approximation is applied to the problem of obtaining minimum distance of two convex sets. Okay, this is what we. So here they are looking at a generic problem, minimum distance of two sets. Okay, and this could be interesting also from data science point of view, right? There is something called separating hyperplane theorem. So whether the data class A, data class B is there, and sometimes during classification problem, what I'm really looking for, if I'm looking for a linear classifier, what I'm really looking for a line that hyperplane that could separate these two classes, and this hyperplane becomes a classifier. So next time a new data point comes, if it's on this is the normal that defines the hyperplane. So I will take a dot product of a new. If it makes acute angle, then I will say this, and if it makes obtuse angle, it's negative sign, then I say this class. Okay, but all this is when they are linearly separable by a hyperplane, right? So in this case, now so this is an interesting problem in itself, theoretical problem that given two sets are there, if they don't intersect, if I get a kind of a minimum distance there, and using that I can define some nice, because once I get a distance, then I can define a perpendicular to the distance, and then this is my minimum distance, let's say. Then obviously this I will take this as a normal normal direction for the plane. So that actually defines the plane also that will separate these two classes for me. Okay, so even if they don't intersect, they studied this problem, right? In our case, it's about the intersection. So both way it works, right? So specifically, given a closed convex set in the Hilbert space, so Hilbert space is a slightly more general space. Okay, it's like more of a function space. Spaces are also used there, but for our case, we can just stick to like metric space. Let P be the map which associates with each point x, the point Px of the K closest to x. That P is well defined. Okay, so that P is well defined, and all this is well defined because of the closed and convexity. Okay, so they refer to some other paper that okay, this is, in fact these things are in textbook also. So P will be called the proximity map of K. This projection is the proximity map. If there are two such sets K1 and K2, then Q denote the composition of P1 and P2 of the proximity max. So as you can see, there are if there are sets K1 and K2, and they are doing the composition now, right? So they said P1, and then after that they apply P2. So basically they are defining this alternate scheme here in the original paper, right? So it is shown that every fixed point of Q is a point of K1 close to this. So basically this alternating idea came from here. Okay, so this is a quite old paper. Now we are in a position to kind of write down the full algorithm. So we want to see whether alternating projection can be used for entropy regularized. Okay, so we have already defined the relations, and this is our entropy regularized problem. And we can start with some initial guess like pi lambda 0, and we set it as p k lambda. Okay, that we defined, right? That with the Gibbs distribution thing, right? So then we have this scheme, projection scheme. Okay, so where we will follow this. So when L is even, then we do this this argmin of KL divergence of pi with this pi lambda L. Okay, let us say in the beginning L is 0, right? So then you start like this, pi lambda 0. So you do this even problem when L is 0, let's say. Then you get pi lambda 1, and then you use that pi lambda 1, and then you get another pi, which is pi lambda 2, I guess, and then you get back to the even case. Okay, so there is this thing missing here. Okay, so this is an odd even scheme where you start with pi lambda 0, which happens to be your original p lambda k, and you keep alternating between these two odd even case, and that's how you keep getting an updated pi. And this KL divergence is acting as a kind of reference point, because it's giving me that because each time I'm kind of like comparing also with the pi. So we have already seen, I have already told you that pi p and pi q are both affine sets. So you can take this as an exercise that these are affine. So that's okay. So then for L even, what we are trying to do is to solve this problem, right? Or basically this problem, right? So basically for even, we can first start with even. We can just focus on the even part. That this is the optimization problem we want to solve. So I drop the KL right now. Okay. So what we have is that there is a equality constraint that needs to be maintained. Okay, so let us focus on the even one, because odd will be symmetrical. Okay, so this is the so we can use the Lagrange multiplier, right? Because this is a equality constraint. So equality constraint goes into the goes as a Lagrange multiplier, like so here, and where f is the Lagrange multiplier, and pi 1m was p, right? So in the Lagrange multiplier, we put this in standard form first, minus p, and then we multiply with the f transpose, right? And this is what is written here in terms of inner product, right? So and we have strong duality, right? So strong duality came from Slater condition, right? I mean, one possibility is Slater condition, right? So Slater condition. So now the question is whether, so Slater condition, we needed f to be objective to be convex, and if we were inequality constraint, then the inequality constraint is strict, right? For there exists an x for which fix are the inequality constraint. These are strictly less than 0, right? But in our case, objective is convex because this is OT with thing. The OT with strong entropy regularized is strongly convex. So our objective is strongly convex, and there are no inequality constraints. So they are all equality constraints. So by default, Slater condition holds. So in this case, strong duality holds. Now we also saw before that if strong duality holds, then we can interchange mean and max. And we will now put the mean here. Okay, that's what we will do. We will interchange that. So then after interchanging, we only look at the mean one. Okay, so let us say you move this guy here and forget about the max for the moment. Just look at the mean one. Okay, so then we are looking at the mean problem, and now to minimize this, right? It's an optimization problem, so we do the first order optimality. Take the partial derivative with pi, and because pi is the variable, right? And equate it to 0. Okay, so we do the first order thing. So we take a derivative of this and with respect to pi and equate to 0. So then what do we get? Our d, which is KL divergence, is this, right? And what is our current pi? Our current pi is what we are looking for will be one more than the existing pi. So our existing pi is pi L lambda, and what we are looking for as a next step is pi L plus 1 lambda. So we could essentially change this this pi that we have to pi L plus 1 by the pi we can change it to pi L plus 1. Okay. So if we do that, then in the derivative we have this. We have pi L plus 1, and I compare it with the current pi, and then I take a derivative with respect to the new pi that I'm going to find. So hence it's L plus 1, and then yeah. So and here it's just the expansion of that, right? So this is whole thing is this guy, right? So wherever I have pi, I put a pi L plus 1. Okay, because it's some operational problem in pi, and some current is there, and what I'm looking for is a new one. So for the moment I keep a notation L plus 1 because this is what I'm looking for, and then using the KL, I mean this is the definition, right? So wherever I have pi, I put L plus 1, and here also L plus 1, and lambda here, lambda here. So if you see that I have written that here. So pi L plus 1 xy log pi xy, and then I have subtracted this also, which is this, and I am looking only at the first term. So I am looking only at the KL divergence term. That's why you see only the first term here, only the first term. Okay. So this part is okay. We have split that, and then if you do the calculation of the derivative, then what you get here is derivative of this guy with pi L plus 1, right? So first first function, if you take the product rule, so first function and differentiation of this will become 1 by pi L plus 1. So that 1 pi L plus 1 get cancelled, so that I get 1, and then second function and differentiation of the first. So that gives me the second one, because it is of the form x log x, right? So essentially we are doing that. And then for the second derivative here, yeah, this is with respect to pi L plus 1, right? So since this is with respect to pi L plus 1, only thing left after derivative is log pi L xy. So that's we have written here. I'm almost done. Okay. So this is, so then we also look at the second term. In the second term we have derivative with pi L plus 1. So basically pi L plus 1 only lies here, right? So this would mean that it will just give me the derivative will just give me minus f in this case. Okay, if we fix it for some x and y, then since I'm looking only at along the x right now, then it will just give me the f component here. So combining both 5 and 6, and we wrote this in a combined form. This is the second term derivative, and this is the first term derivative, and if it was equal to 0, and then we solve for pi lambda this term here. If we solve for this, is a simple algebra is there. There is nothing difficult here, so you can work this out, and you will solve for this exponential f x minus 1, and since pi L plus 1 lambda must be in pi p, the sum, or it should have the marginals p, then in that case the sum, the px could be written as the sum of this, and if I am doing a summing up the y, right? So if I am summing up the y of pi, then I must get a p, because it was supposed to be in pi p, and if that is the case, then pi L plus 1 we have derived from the previous slide is of this form. So pi L plus 1 is pi L times E f x. So that's what I have used here. Pi L plus 1 is like this. It's just that we are also doing the sum right now. Okay, from there I can solve for e to the fx minus 1, and thus we have this. We can now write this because the e term we have calculated as this, right? So remember previously we did this calculation, and we had a e term here somewhere, but then that gets substituted here right now. Okay, so that's so if you go back, this guy, right? So we have found an expression for e, right? We have found an expression for e fx term there, and so basically we substituted that e term there in the ratio. So that was e. This guy was equal to e. So we just make it equal here, and then we solve for pi L plus 1. Okay, these are simple calculations, and we do the same for the even part. Okay, so so you can, because we wrote this in a generic way, it's not really dependent on even or odd. So wherever you have L plus 1, you change it to 2L, and L to 2L minus 1, and to make a even and odd iterations. So L plus 1 to 2L, right? So L plus 1 to 2L, and L to 2L minus 1. Okay, so even iteration will depend on odd iteration, which is just one behind, and so that makes sense. So this is fine. Even the current 2L is depending on 2L minus 1, and similarly for the other guy. And yeah, and I did a vectorization of that. So this was all happening with x and y, right? So you can make them into a vector. Okay, you can also make them into a vector. So we can kind of vector, because it is true for all x and y. Okay, so this whole iteration is running with matrices. Okay, but so we can flatten this and make this into a vector, like so. Okay, so in the vector notations, instead of px, you have p, and this is a point-wise divide. This is not the normal divide. Okay, so entry-wise divide, and this is a vector, because matrix times vector is a vector. This is a vector, so this is a point-wise divide, and this is a matrix. Okay, so even, and then you diagonalize it. This is all coming from this vectorization thing. Okay, you have to emulate the same way like it was done in a pointwise. So you have to do these tricks: make a vector, do pointwise divide, then diagonalize, because it will help in the cache and all this, right? If you do these vector operations, but eventually what you get, obviously, is a matrix. Okay, so eventually it's a matrix. Similarly for the odd iterations, you can see the idea is similar, and then and the whole idea is now simple, right? So you do this pi 0, you calculate this pi 2L, you update this pi 2L plus 1. Okay, and this algorithm is supposed to converge in the sense that the final pi star that you will get will be the optimal one. This will belong to the one with P and Q, and it is the one that's kind of like minimizing your KL divergence also, because that's how the KL divergence is putting this thing, right? KL divergence eventually is linked to the OT problem. So there is a connection, right? So this is not going into the intersection only, but it's also going. It is also solving our OT with OT problem, right? So overall, this is the scheme. I have few things left to make this simpler. This is the matrix based iterations. But we may make this into more. The algorithm will be exactly the same, but it will lead to similar solutions, but it will be more efficient, because it will run with less complexity. Right now we are accessing matrices. So I guess this is the end. So more or less we are done with this. We will need 10 minutes to complete this part. Okay then. So thanks.